Hello everyone, this is lecture 9 of course B645. In the previous lectures, we have covered multiple aspects in the Radiomics workflow using artificial intelligence, from acquiring the datasets to train, validate, and test the model and report the different performance metrics, pathing through selecting Radiomics features, pre-processing, and creating the model and selecting the best model according to the performance metrics. Also, we covered different handcrafted features such as first order features, second order features, and higher order features. Also, we covered local binary pattern and mentioned that you can apply the local binary pattern on the original image and extract different features from the output from the local binary pattern. Also, you can combine multiple features from different aspects together and provide them to your machine learning model or your workflow, aiming to get higher performance. So in today's lecture, we are going to cover a new type of features called shape features. But before describing it, let's focus on this image. Let's say these are normal cells and these are cancerous cells. And I may ask you, what are the differences between both types of cells according to the shape? You may say that most of the normal cells are like circles or ovals. On the other hand, for cancerous cells, they look like non-oval or non-circular patterns. We can define them irregular patterns. So, depending on the shape, you may differentiate between the normal and cancerous cells without getting in depth inside each cell or the different pixels of the images or the relationships between the pixel and the neighbors. So we can simply, based on the shape, can discriminate between normal cells and cancerous cells. And here comes the benefit of shape features. So shape features are critical components in image analysis and computer vision, especially when working with region of interests. These features will help you to characterize the geometry of objects within an image, and this will be useful in various applications such as medical image analysis and pattern classification. So simply, for medical image analysis, you can use shape features to provide critical information about the anatomical structures, pathological changes, and other relevant entities within the image. Also, you can use these features to discriminate and differentiate between normal and abnormal tissues, classify diseases, and even in guiding treatment decisions. So here we need to understand how can we extract the different shape features from 2D images and the 3D volumes. So let's begin with the common shape features for 2D. One of the things that will help us to capture the different features is to calculate the moments. And moments for an image or for a matrix are mathematical quantities that describe the spatial distribution of pixel intensities in an image. And you can think that moments are weighted averages of pixel coordinates, where the weights are typically the pixel intensities. You can obtain the moments using this general formula where P and Q here are non-negative integers representing the order of the moment. So if I said B equals 0, Q equals 0, then it will be M00, which is here. This will be the zeroth order moment. And if 10 or 01, this will be the first order. And if 20 or 02 or 11, this will be the second order, and so on. So depending on the sum of P and Q, we can determine the order. So what's the formula? It's the summation for X and Y. And here you are getting the coordinates multiplied by the pixel intensity at the position X and Y. And here X is raised to the power of P, Y raised to the power of Q. So if you need M00, which is the zeroth order moment, you substitute here by 0 and 0. And simply, this means that you are ignoring both of them. And the final result will be the summation of all pixel intensities. It's like you are getting the summation or the area of the shape. And hence, the zeroth order moment represents the total mass or area of the shape, which means the total sum of all pixel intensities. And the first order assumes that you are setting P with 1 and Q with 0, then this factor will be ignored. Then it's like you are multiplying a weight here by the intensity. Then the first order moments here represent the weighted sums of the X and Y coordinates respectively. And here we use both of them to calculate and compute the centroid of the shape. For higher order moments, you can capture more detailed information about the distribution of the shape, such as the spread, orientation, and elongation. So simply by calculating the different moments, we can use them to calculate the shape features. This is a summary of the first 6 shape features, starting with the area, and here we are counting or getting the total number of non-zero pixels within the shape, and here we are providing a measure of its size, the perimeter, which would be the length of the shape's boundary, the centroid X and centroid Y. Here we are identifying the geometric center of the shape by simply getting M10 divided by M00 so that it can be normalized, and here for Y M01 and divided by M00. So here we are getting the centroid X and centroid Y. Also, the bounding box X, Y width and the height. Here we define the smallest rectangle enclosing the shape, and we are familiar with that when we got the ROI using the bounding rect function in Python, the aspect ratio, and here we are getting the proportion of the bounding box width to the height, compactness, and the compactness here is a measure of how closely the shape resembles a perfect circle, where higher values for the compactness means or indicate greater circularity, and it's calculated by simply getting the perimeter raised to the power of 2 divided by 4 pi multiplied by the area. So by using the area and perimeter, we can make them a composite feature in the compactness. The next 5 features are eccentricity, and here we are reflecting the deviation of the shape from being circular based on the normalized second order moments, and it's the square root of 1 minus M02 divided by M20, convex hull area, and here we are calculating the area of the smallest convex polygon enclosing the shape, highlighting its overall spread. And simply we can do that by getting the contour area of the smallest convex hull, and we will know how to do that programmatically. The extent, and it's the ratio of the shape's area to its bounding box area, width multiplied by the height, and this will indicate how efficiently it fills the bounding box. So if both of them are equal, then the result will be 1, and this means that the ROI fills the bounding box. It's like that the ROI a rectangle, solidity, and here we are calculating the ratio of the shape's area to its convex hull area, and this will present the existence of any holes inside the ROI, major axis lengths and minor axis lengths, and here we can use these 2 formulas to get the length of the ellipsis axis that best fit the shape, and this will capture its elongation and orientation. The next 5 features are orientation, and here we are getting the angle of the major axis relative to the horizontal axis, and this will provide insight into the shape's primary direction, and you can use this formula. The roundness, and here we are measuring how closely the shape resembles a perfect circle, and this feature is complementing the compactness. If you notice here, the compactness has this formula, while the roundness has this formula. Horizontal symmetry and vertical symmetry, and here we are measuring the degree of symmetry along the respective axes, while the overall symmetry combines these scores together for a comprehensive assessment. Elongation, and this will be the ratio of the major axis length to the minor axis length, and this will emphasize the shape's stretching by dividing the major axis length on the minor axis length. Then thinness ratio, and here we are assessing how thin or elongated the shape, and this can be calculated by comparing the perimeter square to the area. The last 3 features are convexity, and here we are measuring how closely the shape resembles its convex hull, where lower values indicate more irregularity, and simply we can divide convex hull area by the perimeter. Sparseness, and here we are measuring how sparse out the shape is within its bounding box, and this will reflect the distribution, and you can use this formula. The curvature, and here we are capturing the average bounding of the shape's contour, while the standard deviation curvature measures the variability in bending, and both of them are highlighting the local irregularities, and you can use this formula. By combining all of these features together, then we are getting insights on the shape features for the image in hand. Now we need to apply the different features, including the geometric and shape-based features on a 2D image. So, good script 31, shape features extraction for 2D. First, we imported the necessary libraries, such as OS, CV2, and the helper functions file. We first got the two images, as we did in the previous scripts. For the image and the segmentation, it checked that both of them exist, read both of them in the grayscale, applied bitwise and to get the ROI, and then calculated the bounding box to get the cropped version from the image. It checked that the cropped version contains data. Then we called shape features 2D to calculate the shape features for the cropped matrix, and it will get the shape features and then print them on the command window. We created this function in the helpers file. As you see here, shape features accepts the matrix. The rest is it checks the matrix is not empty, and then it will start to calculate the features one by one. We use the function count non-zero to calculate the area, then to get the contour and the perimeter and the dependent features that require the contours, we use the function find the contours to find the different contours inside the image. Then we got the maximum contour, which would be stored here in the largest contour according to the area. Then using the function arclength for the largest contour, we'll get the perimeter. Then we use the function moments to extract the different moments for the matrix. To get the centroid x and centroid y, we divided moments m10 by m00, and for centroid y, m01 by m00. Then we got x, y, width, and height from the bounding rect function. The aspect ratio will be the relation between width and height, and compactness is the perimeter squared divided by 4 by area. The centricity will be 1 minus m02 and m20, and here we are computing the normalized second order moments mu to 0 by dividing mu to 0, and here will be the normalized version, by m00, and here m02 by m00. To get the convex hull, there is a function called convex hull that accepts the contour and will return the smallest convex hull, and we can calculate the area again from the convex hull by using the function contour area. The extent will be the area divided by width multiplied by the height. Solidity will be area divided by the convex hull area, which is created here. Measure axis length will be 2 multiplied by the square root of m20 divided by m00, and the same for minor axis length, and here instead of m20 we are using m02. The orientation is 0.5 multiplied by the arctan or tan inverse of 2 multiplied by the normalized of m11 divided by the difference here. The roundness is 4 multiplied by the area multiplied by pi multiplied by the perimeter square. Then to get the symmetry, we use the function flip left right and flip up down for the vertical version. Then we checked for the symmetry in the horizontal axis that both matrix and flipped horizontal divided by the area, and the same for the vertical. And to get the overall symmetry score, we got the average between the horizontal and the vertical symmetry. The elongation is the major axis divided by the minor axis lengths. Thingness ratio is perimeter square divided by the area. The convex hull perimeter is arc length of the smallest convex hull. Convexity is the perimeter divided by the original perimeter of the contour, or the ROI. The bounding box area is width multiplied by the height. The sparseness here uses that area to calculate the sparseness. The curvature is calculated by looping on the different points in the contour, getting the current point, the previous point, and the next point, and using the three of them, we can calculate the vectors v1 and v2 from point 2 and to point 1, which is current and the previous is vector, another vector between the next point and the current point, and using these two vectors we can get the cross and dot products, and then get the angle between them by dividing cross product by the dot product and getting the tan inverse for them to get the angle. So now we have the angle. We will append each angle for each point according to its previous and the next points. Then to get the average curvature of the whole contour or the whole points in the contour, we will get the mean value of them, will be stored here and the standard deviation of them. Based on these all features, we will store them in a dictionary that will be returned back by calling that function. As we mentioned, we printed the different features here. By executing the code, we will get these different features. So simply, by getting the shape features for different images, we can simply compare between them. Maybe according to the compactness, maybe according to the elongation, and so on. Now we need to do the same, but for 3D. Before going to calculate the different features for the 3D volume, let's introduce a package called premesh. And we are introducing that package because we don't need to apply the shape features manually on each image and then getting the average. But here in this case, we need to calculate the shape features of the whole volume as one slot. So to do so, we need something to get some features or some elements or some attributes for the volume. And this will be done using the premesh package. Because if you remember, in the previous code, we required a contour around the lever. So how to do that on the volume? Instead of crafting it from scratch to create a contour around the whole volume, we can use a pre-built package such as a premesh to do that, and we can extract the contour or the element, and based on that we can capture the different shape features to facilitate the coding for us. So to use this package, you need to install it using the pip install premesh pip command. You can use this version 4.4.1 or any recent version from the premesh package. So the aim of the next code is to pre-process and analyze the 3D medical imaging data using the premesh library, and then extract the object and visualize it in front of us. So go to script 32 3D mesh visualization. We imported the premesh package and the helper file, and here we used the read volume, and it worth noting that we have updated the read volume function to include a third parameter here called raise errors, and the raise errors in the read volume will be executed here. So if you need to raise errors or the raise errors flag is true, then it will raise error, otherwise it will ignore that and continue to the next one. By all means, we have the volume grouped, and we need to use that volume grouped to get the mesh and visualize it in front of us. So we will use the premesh package using the function matrix to marching cubes that will return a mesh, and we use the same function to visualize it in a resolution 500 by 500. And by executing the code, you will get something like that. It will open a panel here or a GUI window in front of you that you can simply drag the shape around its axis using the left click and zoom in and zoom out. And if you notice, these are different perspectives from the shape. And we mentioned that we use the function to get something called the marching cubes. So simply the situation here for the package is that we have different slices. For each slice, there is an ROI. And to make a 3D visualization from these slices, simply the package tries to get a cube, let's say it's 1 by 1 by 1, and concatenating these cubes together to fit these slices. So let's assume we have a cube, another cube, a third cube, and so on, until you are completing and fitting the whole volume. So this will be the aim of the marching cubes function. It takes the slices and tries to get cubes with specific dimensions and fit the whole slices together to get a 3D volume in front of you. Now we need to extract features from that mesh. There are different common shape features for 3D, such as the volume. We are getting the summation of the non-zero voxels in the 3D volume, and we are saying here voxel because we are dealing with X, Y, and Z. A surface area is the total surface area of the triangular mesh, surface to the volume ratio, and here we are dividing the surface area, which is here, by the volume, which is here. Compactness, again, it's how closely the shape resembles a perfect sphere, not a circle in this case because we are in 3D, where higher values for the compactness indicates we are getting closer to the spherical form, and this will be the volume raised to the power 2 by 3 divided by 6 multiplied by the surface area multiplied by the square root of pi. Sphericity, and here we are evaluating how spherical the shape is by using this formula. Also, we can calculate the elongation by comparing the longest dimension of the bounding box to the shortest dimension. And here we are evaluating the stretchness of the shape. Flatness, where we are measuring the degree of the flattening in the shape by comparing the shortest to the intermediate. Rectangularity, here we are assessing how efficiently the shape fills its bounding box by dividing the volume by the product of the dimensions. The Euler number, and here we are describing the topological characteristics of the shape, such as the number of connecting components and holes, and this will reveal the structural complexity, and this number is calculating from the mesh or the tri-mesh package automatically. So now we need to use these features and apply them on the mesh, and you know how to do that, aiming to extract features from a 3D volume. Remember again to apply padding to unify the shapes, as we did in the previous lectures. Now, with script 33, shape features extraction for 3D, we imported the OS library and the helper file. Then we defined the range for the slices to be processed, and here we picked the slices that contains content or pixels, ignoring the black images. Then we got the files, applied them to the read volume with ignoring any errors to get the volume grouped. Then execute a function shape features 3D to get the shape features and then printing them on the window. This function starts by getting the mesh using the matrix to Martian cubes function from the tri-mesh package. Then we started to calculate the different features. First, the volume will be the summation of the given matrix or the volume. The surface area is assessed by accessing the area from the mesh here. The surface to volume ratio is the surface area divided by the volume. Then we calculated the compactness, sphericity, and the different dimensions, minimum, maximum, and intermediate. Then we calculated the elongation and the flatness. Then we calculated the rectangularity by dividing the volume by the volume of the bounding box. Then we use Euler number from the mesh to get the Euler number, combined all of that together into a dictionary to be returned here and printed. When you execute the code, you will get the following features, as you see here. Again, you can compare different features together. Maybe you can get the 3D features for a normal cell and a cancer cell and compare between both of them together. After knowing how to extract the shape features for 2D and 3D volumes, let's go to an example. Here, we are acquiring the dataset from a website called Zenodo. We knew how to deal with Kaggle to download a dataset. Zenodo is another platform to share your data, your code, and publications. We will download the MedMNIST Plus database from that website, which was originally made by Yang et al. This database includes more than 18 standardized datasets for 2D and 3D biomedical image classifications with different shapes. So you can use that to validate your model. Maybe you can create your framework and you need a ready data set to be used, whether you need a 2D or 3D. So you can use this data set as an example for your framework or your approach. Inside it, you will find different data sets as mentioned, such as MedMNIST for chest data, OCT for eyes, and retina for eyes also, derma for skin, and so on. You will find data for 2D here, and for 3D, you will find a postfix here with 3D. So these data are for 3D and these data are for 2D. When you scroll on the website, as mentioned here, you can download the different data sets with the different sizes using the download link, and these are the corresponding sizes. For example, for the chest MedMNIST in 2D version, it comes with different sizes such as 64, 224, 128. The same for nodule MedMNIST 3D and organ MedMNIST 3D. You can download 3D volumes, and all of them are in the NumPy compressed file here in BZ, or you can install the MedMNIST package using the pip install MedMNIST command and let it download internally the dataset by itself. So now you have different approaches, whether you download it manually or automatically using the package. So go to script 34, 3D shape features example on MedMNIST. And here we are importing Adrenal Menis 3D, and it will download it automatically if you are calling the function or the class. If you are calling it and setting the flag download equals true. Also, it provides you which split do you need. Do you need the train, the validation? Here we are accessing the validation. So we are storing it in the validation dataset. You can get the number of samples. You can access the sample shape, the minimum and maximum values. And here we are accessing it using 3 indices, 2 indices to get the full images, and a third index here to access the first image in the validation dataset. First, we loaded the first sample from the validation dataset and calculated the minimum and the maximum to normalize it and convert it as unsigned integer to be converted so that we can calculate the shape features 3D on that volume. We executed the shape features 3D function that got the shape features. Then we printed it on the command window. Also, we visualized the volume by getting the mesh using the matrix to Martian cubes function from the try mesh package. Then we defined set of commands. First, we set a uniform color for the mesh to be light gray using face colors and providing RGB A, and here is the A channel for full opacity. Then we enabled the smooth shading for better visualization. Then we created a scene, and from that scene, we displayed it in 500 by 500 resolution size. Before it, we made the camera to look at these points for better visualization. So here we are adding directional lighting to the scene. So you can use that for better visualization, because sometimes when you visualize something small using the try mesh, it becomes black or very dark. Then you can here apply a smooth shading and light gray or uniform coloring and change the position of the camera so that you can get better visualization, but it will not affect any features. When you execute the code, you will find something like that. It's something like grayish color or light grayish color, and it reflects the adrenal gland. And here the first sample from the validation dataset with different perspectives, and the adrenal gland anatomically will be found above the kidney. So simply, if you have different classes according to some cancer or tumor in the adrenal gland, then you can extract the different features for each class, as we did with the 2D in the classification lecture, and extract the shape features for each and compare them together using a classification model and optimizing that model to get high performance, for example, high accuracy and high sensitivity. And if you notice here, we have 98 in the validation subset, where each of them has a shape of 28 by 28 by 28. It's like a cube. So in this lecture, we have covered the meaning of shape features and how to extract the shape features for 2D images and 3D volumes. Then we went through a dataset that can be used to validate your work and framework, which is the MedMNIST Plus database that can be downloaded from Zenodo. And Zenodo here is a platform that you can download publications, papers, and code from it, shared by different authors and researchers. Then we emphasize the role of the try-mesh package that can convert the slices for the 3D volume into a real volume using the Martian cubes approach. And you can read more about the Martian cubes and how it's built from scratch. And finally, we highlighted that we can combine the shape features with other features and apply them to our machine learning framework or AI model, and try to optimize that framework, aiming to get a high performance such as accuracy and sensitivity.